Okay, we are in section 6.4, harmonic motion. Harmonic motion. Now, I'm not going to write these problems down because they are long and the descriptions are long. So what I've done is I've posted in the homework week 10 folder 6.4 textbook. And so what I've done is I've copied those first 4 or 5 pages out of section 6.4. So you will need to open that right now so that you can see what I'm talking about. So open up 6.4 and you'll see that section, or open up your electronic text, either one you want. And I'm going to ask you to just follow along here because I'm not going to write down these examples. I'm not going to write down their description of simple harmonic motion. I'm just going to use it. So again, open up the text, look at this information, and follow me. And again, I've made a copy of that and put it in our week 10 folder so you can look at that, and then, or while you watch the video, maybe print it out and watch it along with the video. So they talk about, if you look at this very first example, simple harmonic motion, and an example might be a spring, right? If you've got a spring and you've got something attached to the spring, you pull the spring and then you let it go, well, it's gonna just go up and down and it's gonna oscillate. Well, things that oscillate are very easily or very appropriately described by either the sine or the cosine function, all right? This is called harmonic motion, all right? And this is the spring at rest, and maybe this is the spring stretched all the way out, right? And in between, it's not quite, and you see the picture, it's gonna, when you stretch it out and let it go, it's gonna do this and just go back into a state of rest. So again, you can look at the picture and you can read the initial stuff. So it says the spring is displaced A units up. So if you push the spring A units up and let it go, then it's going to come down, then it's going to go back up. It's going to keep doing that until it finally balances itself and gets back at rest. So again, I'm going to refer you to that very first picture, that first paragraph, where they talk about all this stuff. They say the constant omega is generally taken to be positive and related to the period P. The period is the time required to complete one up and down cycle. That's important. Period P is the time required to repeat, to complete one up and down cycle. In this case, that'll be the period. The time required to complete one up and down cycle. Start at a point, it goes up, comes back down to that same point. That is the period P. The frequency, and again, these things are defined and listed out on this sheet. They say the frequency, F, so the way we denote frequency is lowercase f, is the number of cycles, the number of complete cycles completed per unit time. It's the number of complete cycles. All right, per unit time. Per unit time. All right. And they tell us in this box, simple harmonic motion. It says if the displacement d of an object at time t is given by d equals, so there's a couple of these guys, d equals a sine omega t, or d equals a cosine omega t, all right? They say the amplitude of motion, the amplitude is just that distance that it vibrates up and down. It's going to go A in a positive unit, A in a negative units, A in positive units, A in negative units. It's going to keep repeating that until it kind of dampens itself out and comes back to a state of rest. So A is the amplitude. Okay, that's what that A stands for, the amplitude. And they say that the period P is 2 pi over omega. P is 2 pi over omega. where they say, and again, that's the time to complete one cycle. That's the same thing here, same period we're talking about, but I can write it as 2 pi over omega. And they say that F equals 1 over P. Frequency is 1 over the period. And they say that F equals omega over 2 pi. All right? And if you want, you can say that omega is 2 pi over P. Okay, omega is 2 pi over P. You get that from here, just solving that equation for omega. All right? Or, if you want, you can say omega is 2 pi F. All right? So if I use that, then I can change these guys. So these are my models. This models that simple harmonic motion. But if I use the fact that omega is 2 pi F, I can replace this and say that D equals a sine omega t, or not omega. I'm using 2 pi F for omega. So I can get that t, or D equals a cosine 2 pi F t. So there's an alternative way to write my equations that describe simple harmonic motion. Again, A is the amplitude that starts at 0, goes up A units, then back down, and then back down A units. Positive A, 0, negative A, back to 0. That would be one period. All right. So again, read this information a little bit, get yourself familiar with what these variables mean. Let's just do an example. We're going to do example 1, and again, I'm not writing this, so read through example 1, and I'm going to help you understand it. So I'm just going to write example 1, and I'm going to start talking about what all this stuff is. So example 1. It says, this is example 1 in your textbook in section 6.4. It says, suppose that the block at the end of the spring in figure 6.26. So what that is they go back to the very beginning of section 6.4 and they reference this picture. So go back and look at that picture. This picture is being referenced by example 1. Suppose the block at the end of the spring in figure 6.26 is originally compressed 10 inches upward. All right. What is the period of motion? And after release, the block makes one complete down and up cycle. One complete down and up cycle in 0.5 seconds. So A says, what's the period? Well, if they said it makes one complete up and down cycle in a half second, that's exactly the period. So the period is 1/2, or 0.5 seconds. That's exactly what the period is, the time it takes to make one complete up and down cycle. So the period would be 0.5. What's the frequency of motion? Well, the frequency is always 1 over the period. So B says, what's the frequency? The frequency is 1 over the period, so that'll be 1 over 0.5. All right. 1 over 0.5 will give me 2. Okay? And that'll be, the units are, again, a frequency of 2 means that you complete 2 cycles per unit of time. And this guy, the block, they say made one complete down and up cycle in 0.5 seconds. So our units of time are seconds. So this thing completes 2 cycles in 1 second. And we usually write those units as hertz. So the frequency would be 2 hertz. Again, the frequency is just 1 divided by the period. C says, what's the amplitude? C says the amplitude, little a. Well, they told us that the block was originally compressed to 10 inches upward. So the amplitude is actually the absolute value of A. I should have absolute values there. But that's the absolute value of 10, which is 10 inches. That's the amplitude. And then they say, write a function D says write a function of the form D equals A cosine. So D, write a function of the form D equals A cosine. They say omega t. All right. To model the displacement in inches of the block as a function of time t seconds after release. All right. T seconds after release. All right. Well, so all you're doing is plugging in. We know what A is. A is 10. Omega, again, we could use this guy to rewrite omega. Omega is the same thing as 2 pi f, and we know what f is. F is 2. So I could rewrite this as D equals A cosine of 2 pi f t. And then plug in what you know. A is 10. Cosine 2 pi. F, we already determined was 2 t. So D equals 10 cosine 4 pi t. That would be the model. That's the answer to D. And finally, E says find the position of the block 6.25 seconds after release. So we said that T equals 6.25 seconds. So all you're doing is plugging 6.25 into this guy. So 10 cosine 4 pi times 6.25. All right. And if you do that, do the math, G equals 10 cosine. 4 times 6.25, that's 25 pi. All right. Cosine of 25 pi is the same thing as cosine of pi. You can take out all the multiples of 2 pi, remember? Cosine repeats after every multiple of 2 pi. So this would be the same as 10 cosine of 1 pi. Take out the 24 pi, because it's just going to keep repeating. It's a cyclical thing. Cosine of pi is -1, so you get -10. So -10, let's remember what we did. We took a block at the end of a spring, we compressed it 10 inches upward. We let it release, and after 6.25 seconds, the position of the block is -10. And all that means is that block is now 10, and these were inches, 10 inches below the equilibrium position. The block is 10 inches below. That's the key word. That's that minus sign. That minus sign tells us it's below the equilibrium position. Okay? The block would be 10 inches below the equilibrium position. Okay? So that's how these problems are going to work. I'm going to use one of these two models, right? And you're going to have to determine the amplitude, the frequency, and again, if you get the period, the frequency is 1 divided by the period. And then you'll have a functional model, and then you can use the model to actually find where the position of whatever the thing is, in this case it was a spring, after 6.25 seconds. So that's how that works. All right, let's do another example. And we are not going to do damped motion. We're only going to look at the very first part of this section. Let's look at example 2. So again, look at the third page that I posted, or in section 6.4. Look at example 2. And again, I'm not going to write it. It's right there for you, or it's in the book. You can open up the book, electronic book, and look at it. This says a Ferris wheel is 150 inches. A Ferris wheel is 150 feet in diameter, with its lowest point 3 feet off the ground. And they show us a picture of that Ferris wheel, right? You can see a picture of the Ferris wheel, so make sure you look at it. A Ferris wheel is 150 feet in diameter with its lowest point 3 feet off the ground. Once all the passengers have been loaded, the wheel makes one full rotation counterclockwise in 2.5 minutes. Once the passengers have been loaded, the wheel makes one full rotation counterclockwise in 2.5 minutes. Okay? Well, they just told us the period. The period is 2.5 minutes. Write down the information as you're given it. The period is 2.5 minutes. It makes one complete rotation. That's exactly what the period is. So the period is 2.5 minutes. Okay? They say, suppose that two children are seated at the lowest point on the wheel and are the last passengers to be loaded. Okay? So again, take a look at that picture. So you got to imagine that these kids are at the bottom in that very lowest cart right there. That's where they load them up. All right? And they say, choose a coordinate system with the origin at the ground level and below the center of the wheel. So A says, write a model representing the children's horizontal position, Horizontal position means the x-axis, horizontal, okay? Write a model representing their horizontal position, x in feet at a time t after the ride starts. So the roller coaster is 150 feet in diameter. Its lowest point is 3 feet off the ground. And if you look at this picture, they show you they're going to consider the origin to be at the bottom of that very lowest cart. So that's where the kids enter. That'll be the origin, 0, 0. X is 0 and Y is 0. And this guy is turning counterclockwise, so it's doing this, going counterclockwise, all right? So I want to write a model representing the children's horizontal position in feet at a time t after the ride starts, all right? So I got to imagine myself, the kids getting in the cart, and again, they start at x equals 0, and then they start going around. So they start here, then they go around counterclockwise, and again, this thing is 150 feet in diameter, so if this is x is 0, if they go out, this thing is going to keep going like this. So if this thing is 150 feet in diameter, then the distance from here to here is 75 feet. So when they get right here, they've traveled 75 feet in x. They go from x equals 0 over here to x equals 75. That's the position of the cart. That's 1/4 turn. Then when they go from here to here, they went from x equals 0 to 75 from here to here. Then they go back to x equals 0 because you come in, again, we're doing horizontal position only, so left and right. They started here at x equals 0. They went out to x equals 75 right here. Halfway on the ride, they're back at x equals 0 because this is at x equals 0 again. Then 3/4 of the way, they're 75 feet to the left of their initial position. Because again, that's 75 too, right? And then when they come back and complete the rotation, they're back at x equals 0. So they start at 0, go up to 75, back to 0, go back to negative 75, and then back to 0. So if I think about that, x only, start at 0, go up to 75, back to 0, down to negative 75, back to 0. Okay? And this will be completed in t equals 2.5 seconds. This axis is going to be t. This axis is going to be height. So they start at 0, it's right here. They go 1/4 of the way, they're right here at the top of the ride. Or at x equals 75, I'm sorry. When they get to the top of the ride, they're back at x equals 0. So this axis here is x. They start at x equals 0, 1/4 of the way, they're right here at x equals 75. Halfway, they're back at x equals 0. That's this one. 3/4 of the way, they go down to x equals negative 75. And then when they get back to here, they're at x equals 0 again. So that's why we can use a sine function to model this behavior. It looks just like a sine function. And again, we're doing horizontal position. This chart is only for horizontal position. I didn't think about y at all. We're going to do y in the next part of the problem. Okay? So, we can clearly see from this chart that the A is going to be, the amplitude is going to be 75. Right? The amplitude is going to be 75. We know that the period was 2.5. So my frequency would be 1 over 2.5. 1 over 2.5 is 0.4. All right? And so now I can use my model D equals A sine. So A is 75 sine 2 pi F is 0.4 T. Multiply the 0.4 and the 2 pi, and D equals 75 sine of 0.8 pi T. There's a model that models my horizontal position. And I should say X. This is X only. This is modeling the horizontal position, X. All right? This is a model for the horizontal position X only. Okay? Hopefully that graph makes sense. Okay? We can clearly see that that graph represents a sine function. It looks just like a sine function, and hence I'll use the sine version versus the cosine function. All right? Now, part B, that part B, they want us to model the vertical position. Part B says write a model representing the children's height, y. Right, model for children's height, y, in feet. Okay, I want to write a model that represents their height in feet. Okay, now let's go back and read the problem one more time. If you start at the very beginning of example 2, it says a Ferris wheel is 150 feet in diameter with its lowest point 3 feet off the ground. If you read the very beginning of the example, it says a Ferris wheel is 150 feet in diameter with its lowest point 3 feet off the ground. So now we're modeling y. So let's just think about how this thing works. The period is still 2.5. 2.5 minutes, not seconds, minutes. I think anyway, right? Yeah, 2.5 minutes, all right? Now, this axis is y now, not x, y. So it says the Ferris wheel is 150 feet in diameter, its lowest point is 3 feet off the ground. So you're starting at y equals 3. That's where those kids are starting, sitting in that little car to take them up to the top of the Ferris wheel. They start off at 3 feet, all right? Now the Ferris wheel is 150 feet high. So they're gonna start off at 3 feet. They're gonna go up, right, to the top, come back down. That's one period of that function, all right? Now it's 150-foot Ferris wheel. So they start off at 0. When they get to the top of the Ferris wheel, they're at 150 feet, but 150 plus the 3 would give me 153. Well, we can clearly see, again, they start at the bottom. The Ferris wheel goes up, so again, they're starting right here, y equals 3. The Ferris wheel goes all the way up to the top. They're at 153, right here. then it goes back down from 153 back to 3. So that's this piece right here. So this half corresponds to this first half corresponds to this travel. One complete period of this function, all right? Now, we need to talk about the amplitude, all right? Well, amplitude is just gonna be this distance divided by 2, right? Because there's my equilibrium. So my amplitude is gonna be the 153 minus 3 divided by 2. Well, that is 75 feet. That is 75 feet. But I gotta be a little bit careful, all right? I've gotta, since again, equilibrium is here, I've gotta take A as negative 75. All right, I've gotta take A as negative 75. And let's see if this is gonna work. We knew the omega, the F hasn't changed. F was still 0.4. F is still 0.4. Okay, F is still 0.4 RPMs, okay? And we can clearly see that's a cosine function. So now Y equals, so I'm gonna have, and I claim it's negative 75, and it's gonna make sense in just a moment, negative 75 cosine of 2 pi F, so 2 pi times F is 0.4 T, right? But remember, at time equals 0, you're sitting right here at 3. So I'm gonna add 78. And let's see if this makes sense. And we can simplify this guy a little bit. And if you wanted to, you could write it like this, 78, not 5, 8. 78 minus 75, cosine 0.8 pi t. I claim that's the model, all right? That's the model. Let's see if it makes sense. At time 0, y should be 3. You're right here. At time 0, before the ride starts, y should be 3. So at t equals 0, cosine of 0 is 1. You get 78 minus 75. So at t equals 0, you'd have y equals 78 minus 75 cosine of 0. But cosine of 0 is 1. So that's just 78 minus 75, which is 3 feet. We had to accommodate for that fact. Okay? So there's my model. 78 minus 75 cosine of 0.8 pi t. And the last part asked me, find the children's position 2 minutes on the ride. Find the children's position 2 minutes on the ride. And that's easy stuff. At t equals 2, 2 minutes, I'm gonna have to calculate it, both x and y. So x, my model for x was 75 sine 0.8 pi t. And my model for y is this guy, 78 minus 75 cosine 0.8 pi t. And all we're doing is putting 2 where the t is. All you're gonna do is put 2 where the t is. So x would be 75 sine 0.8 pi times 2. Y would be 78 minus 75 cosine 0.8 pi times 2. If you do both of those, x turns out to be negative 71.3. Y turns out to be 54.8. So that'll be the coordinates of where they're at after 2 minutes. 71.3, y is 54.8. That would be the coordinates. So again, remember that, again, if this is the origin, positive x is that way, negative x is this way. So x equals negative 71. means they're kind of close over here, and y is a positive 54, so maybe somewhere around here, maybe. All right. So that's all I wanted to do in section 6.4, is show you how to do or to model harmonic motion without damping. So those are the only two examples that you will be responsible for. That's the only two things in the homework. Thank you.